Hey everybody, in this video let's learn how to integrate using U substitution. For example 1, we can see that we have this complicated integrand right here. And we want to figure out, well, what is this the derivative of? What did we have to differentiate to get this derivative? Using the technique of U substitution, we want to kind of linger on the integrand and look and try and identify inside functions whose derivatives are present as other factors. So we can clearly see that we have a power function. So sometimes that might be a good place to kind of start. If the outside function is a power function, take a look at the inside function. Okay, it's quadratic. And the next thing in your brain, be thinking, well, is the derivative of this quadratic function present? Does it appear as a factor? Well, the derivative of 5x squared plus 8 would be 10x. And while we look over here and we see that we have 7x, 7x is not 10x. But we really don't want to concern ourselves too much with constant multipliers because we can manipulate those. We can work with making changes to that. The big picture is this. The derivative of the inside function is a linear factor. Okay, and here we have the linear factor x. Okay, so be patient as we work through these examples. It's not until after probably example 3 that you start to get the feel for what's going on. So try not to groan until after example 3. Alright, so how do we proceed? Well, once we kind of have an idea of what we think is going on in this problem, we're going to come over here and do some side work. I think that the inside function right here, 5x squared plus 8, okay, is where I want to start. So my starting place is going to be designated to be U. So what I'm going to do is I'm going to replace all of this right here with just the letter U to kind of uncomplicate it. So come over here and show your work. So I'm saying that U is 5x squared plus 8. Alright, so now I'm going to say, alright, well, if I bring in the derivative operator with respect to x, okay, if I bring that in, d over dx, this becomes du dx. Okay, and over here it just means I'm going to differentiate with respect to x. So if you want to show this up here, that would be fine. But you don't have to. From this line to this line, if I differentiate with respect to x, then my work would look like this. This would be 10x. Alright, so how we proceed from here is this. We're going to separate some variables here. I mean, look at this structure right here. Let's get du by itself. Meaning I would multiply both sides of this equation by dx. Although not technically correct, because this is a rate of change that we wouldn't separate. Okay, for the purposes of this technique of U substitution, this is how we all proceed. Alright, so we're left with du, and then over here we have 10x dx. I know this seems kind of strange, but like I said, after 3 examples you'll start to get the feel for it. So the first thing is I'm going to allow u to be 5x squared plus 8. I'm going to find the derivative, okay, and I'm going to write it in this format. Okay, so it's going back and forth looking at what we need to do to adjust to get the answer here. Alright, so what you might want to do is this. Rewrite and put the 7x factor behind this quantity here. Just kind of helps us pay attention to what we might want to do. Okay, all I did was rearranged. Okay, why? Because I want to look over here and I'm going to go, okay, well this is 10x with the differential dx, and here I have a 7x with the differential dx. My objective is to change out of all x's here into u's, and when I change out of x's and rewrite using substitution an integral in terms of u, I'm really going to end up uncomplicating, if you will, this integrand. Alright, so what do we do next? Well, what I see is that right here I can pull out this multiplier of 7. I don't want 7, I want 10. I want 10x dx. So here's one way. Okay, if I pull out this multiplier, because I have a property of limits that say I can pull out a constant, okay, I'm going to have 7 times the integral, quantity 5x squared plus 8 cubed, and I'm left with x dx. Okay, so everything so far has been okay. I've rearranged, I've pulled out a constant multiplier. We'll never pull out a variable factor multiplier. We'll never pull that out because that requires some action. So I can manipulate constant multipliers. All right, so I'm at this point right here. I know I could replace this quantity right here with u. So I'd have u cubed. Okay, but then I have a mixture of u's and x's, and that's not what I want. I want everything in terms of u. All right, so I see that du is 10x dx. Well, all I have is x dx. So what I'm going to do is I'm going to bring in a 10. I can bring in or take out constant multipliers, but that's it, not any variables. So if I brought in a 10 here, which wasn't up here on the original line, I'm actually bringing in 10 and then also times its reciprocal 1/10. Think about that. 10 times 1 over 10 is just a clever form of 1. I need 10 here to match this 10. Okay, so if I bring in 10, then I really am bringing in also 1 over 10. Well, with that 1 over 10, it's a constant multiplier, so I'm actually going to pull that out front here and put the 1/10 here. All right, so stop and think and take a moment. Is everything good? Yes, the 1/10 times the 10 would just be 1. I could put the 7 back in, and that would get me to my original line. So I haven't done anything that's like mathematically illegal. I'm just manipulating these constants to get what I want. All right, so here's where we're at. Let's clean this up. 7/10 times the integral quantity 5x squared plus 8 cubed. And I have 10x dx. This is precisely what I wanted. I wanted 10x dx because I want to be able to take du and replace it with 10x dx. Looks like I have everything I need here, so I'm going to proceed with u substitution. Okay, right here I'm going to replace this quantity with u, so I have u cubed. All of this is going to be replaced with du. So I've just switched from an x integrand to a u integrand. Take a look at this right here. Okay, I've just uncomplicated this complicated derivative. If you study this, if you look at how to proceed to integrate it, it's simply the reverse power rule. So at this point right here, I can just see that I have u cubed du. This tells me to find an antiderivative. So proceeding forward, 7/10. Okay, I'm ready to integrate. So this becomes u to the 4th, increase the exponent by 1, divide by the new exponent, and then I also have a plus c. And I'm just going to put the plus c, the constant of integration, right here on the outside. So I'm going to come up here, save some space. And I don't want a u answer, I want an x answer. So all I'm going to do is I'm going to replace the u up here, okay, with what it was representing back up here. So 7/10 times, and I'm going to pull the division by 4 out as a multiplier. So 1/4 times quantity 5x squared plus 8 plus the constant of integration. Okay, now what I could do is I could multiply here, do a little cleanup, so I'm going to have 7/40 times quantity 5x squared plus 8 to the 4th power plus c. That's it. That's our answer. If you wanted to, you could check this answer. So that's what we're going to do here. You don't have to do it for all your problems, but if you're ever at a point and you're going, I don't know if my answer's right, let me differentiate it, you could do that. So let's go ahead and all I'm doing is checking my answer. Let's see if this derivative is what we started with. Okay, if I'm differentiating going forward, I have to use the power rule. So I notice right here that the outside function is 4. So if I find the derivative, I would bring the 4 in front, multiply it by 7/40. So 4 times 7/40. Reduce the exponent by 1 and multiply by the derivative of the inside function. Okay, this is going to be, what, 7/10 times quantity 5x squared plus 8 cubed. This derivative would be 10x. We're going to reach across here and we're going to cancel the 10 factors. And I'm going to rearrange and put the x next to the 7, so I end up with 7x quantity 5x squared plus 8 cubed. If you look back up here, that's exactly what we started with. So this little check right here just should assure you that this technique of u substitution is valid. And the big picture is, what we're doing is we're trying to uncomplicate this integrand by using u, or any other letter, to help us simplify it into something that we're comfortable integrating. If you're still confused, that's okay. After the third example, you're going to get the feel for it. For example 2, our objective is to find the antiderivative. Looking at the integrand, the first thing I'm going to do is rewrite any radicals as fractional exponents. And as I do that, I'm also going to put that first. And I'm going to put the x squared dx here. And the reason I did that is because as I'm looking at this integrand, if I observe that I have a power here, that's kind of a good starting place. If that's the power function, it might be an outside function. So the inside function is where I'm going to look. And if I think about the derivative of a cube, it's going to result in a quadratic. So we want the inside function to be our u. What we did next was we found the derivative with respect to x. So we had du over dx equals 15x squared. We separated and pulled the dx to the other side to get the differential in u by itself. So that's what we did and proceeded over here. So now take a look back here. All right, well, the x squared dx is present here, but I don't have a 15 here. If I had a 15 here, I could replace all of that with du. So actually what I'm going to do is I'm going to bring in what I need. I'm going to bring in a 15 because I can bring in constant multipliers. But remember, that wasn't up here. So if I bring in a 15, I need to bring in a 1 over 15. Well, if I bring in a 1 over 15, I'm going to go ahead and pull it outside here. Because I don't want it here, I have everything I need to replace with du. Looks like we're ready to go, meaning let's change over from an x integral to a u integral. This will be replaced with u to the 1/2. So, and then all of this will be replaced with du. Looking at what we have here to integrate, all right, so our letter of choice is u. Okay, but if we're going to integrate this right here as if it was x to the 1/2, that's a simple reverse power rule. So that's what I'm going to do next. Keep the 1/15. Since I'm ready to integrate, I remove the integral symbol. And remember, when you remove the integral symbol, you also remove the du. So if you want to think of it as just disappearing, sure. But it has to disappear when you integrate and you lose the integral symbol. Reverse power rule, increase the exponent by 1 to 3/2. Divide by 3/2, which is the same thing as multiplying by 2/3. Okay, close the bracket, add your constant of integration. All right, a little cleanup here maybe. I could multiply these two together because 2/3 isn't wrapped up with an exponent. And I'm also going to replace u with what was being, what it was holding up here. So this product is what, 2/45 u to the 3/2 plus c, where u is 5x cubed. That's it. That's your answer. You could spend some time differentiating this to check to see if you get back to this integrand. It should work out. This answer's fine right here. If you wanted to, another form of this answer, okay, would be to rewrite it as a radical. It's this quantity, 5x cubed to the 3rd power, and the square root. So the numerator is your exponent on the inside function. Your denominator is the root. Either one are acceptable. For example 3, let's do a rewrite on it. Meaning let's pull up any exponents in the denominator to the numerator as negative exponents. So I'd have 2x quantity 1 minus 2x squared to the negative 3. All right, looking at what we have here, I see a power function, I see an exponent, so I'm going to immediately, as a first step, just kind of look and investigate the inside function on that power and think about, well, the derivative here would be negative 4x, and although I don't have negative 4x, I do have 2x. Okay, I do have the right variable that I need. Maybe not the right constant multiplier, but that's okay. I can manipulate that. So to me, it looks like my inside function, my u, if you will, is going to be the quadratic function 1 minus 2x squared. Bring in the derivative operator. You can skip that middle step up here. If you want to go straight to du, okay, and find this derivative, it's negative 4x. Just put the dx here. All right, taking a look at what I have, I think I'm going to rearrange it. Put the 2x next to the differential in x and just kind of focus my attention on that because that's where I need to do some adjustments. At this point I need a negative 4. I have a 2. So on this problem, because everything's kind of nice, I think I'm going to bring in a multiplier of negative 2. If I bring in negative 2, that becomes the negative 4 I need. Well, negative 2 wasn't here originally, so to undo that, I'm going to bring in also a negative 1/2. And when I say bring it in, I'm actually going to take it out. So think about these two cancel and everything's still good. All right, I think I have everything I need, so I'm going to rewrite it, negative 1/2 integral. This will be replaced with u to the negative 3. Okay, that product is negative 4x dx, and so all of that gets replaced with du. U substitution helps us uncomplicate an integrand. And when we study this, next we just integrate using the reverse power rule. So I have the negative 1/2. Reverse power rule, increase the exponent to negative 2, divide by negative 2. All right, when I see what I have here, I could pull out a negative 1/2 to multiply by the negative 1/2 here. Think about this right here. So that becomes positive 1/4 times u to the negative 2, where u was 1 minus 2x squared to the negative 2. You can leave your answer like this, or you can rewrite it, pulling down this quantity with the square. So it would go in the denominator with the 4. Either one is acceptable. Just different formats of writing your answer. Again, you could check by differentiating to see if you end up with the integrand, and we should. For example 4, this might be a good time for you to maybe try this problem on your own. So pause the video, try it, and then come back and kind of check, see how you did. Be good for some little independent kind of / guided practice. Okay, so if I'm trying to find the antiderivative, I certainly don't want to expand this 5 times and then do a reverse power rule on all the terms. So we want to use u substitution to help us with this problem. All right, I see a power. I'm thinking the inside function would be my u. Well, if u is 4x plus 3, the derivative would just be 4. So du becomes, the derivative here is just 4 with the dx. The differential on one side requires it on the other, just 4. So, and I can manipulate constant multipliers, so I'm not worried that there's not another factor here. All right, so thinking about where we're at, if u is 4x plus 3 to the 5th, and I have dx, then I need to bring in a 4, which means I'm going to pull out a 1/4 in front. Okay, so let's rewrite it. Replacing 4x plus 3 with u to the 5th. All that gets replaced with du. So we're integrating using the reverse power rule. In this video, all the problems are where the outside function is a power function, so we're going to be using the reverse power rule. In the next 2 videos, that might not be the case. The outside function might be a trig function. All right, so let's integrate. increase the exponent to 6, divide by 6. Okay, I can kind of see that I can multiply 1/4 times this 1/6, so I have 1/24 times quantity u, which was 4x plus 3. You could check your work by differentiating to see how you did. For example 5, you might want to proceed kind of the same way. You might want to attempt it on your own and come back and kind of check and see how you did. All right, studying the integrand, I noticed that I have a power function. The inside function is linear. The derivative of a linear function would be a constant function. I do have a constant multiplier here, so I think the way to proceed with u substitution is to let u be 2x minus 3. All right, the differential in u, or the derivative, would be 2. Keep a dx here. Gotta come over here and look and see what we have. Okay, well, there's really no easy way to make 7 2 other than multiplying by 2 over 7. So what I think I'm going to do is I'm going to go ahead and just pull the 7 out. There's a couple of ways you can handle constants, but I'm going to go ahead and just pull the 7 out. That way I can just focus my attention on bringing in a 2. So noticing that I need to convert to u substitution to a u integral, I need to bring in a 2. I also need to then bring out the 1/2 multiplier. All right, a little bit of cleanup here. This would be 7/2 integral. Everything's ready to be replaced with u. So we have u to the 4th. We'll replace with du here because that's exactly equal to this. We have an uncomplicated integrand. It's a power function. That requires the reverse power rule. So ready for integration. Trying to remember to put on our constant of integration. Reverse power rule, increase to 5, divide by 5. Converting back to the x answer. So I know I can multiply 7/2 by 1/5. That becomes 7/10. Quantity u to the 5th plus c, where u represented 2x minus 3. Again, of course, you can check your answer by differentiating to see if you get back to what you started with, and you should. So hopefully now you have, after 5 examples, become to feel a little bit more comfortable with u substitution. And in all these problems, like I said, we were actually using the reverse power rule on our u integral. Okay, it's not always the case that we use reverse power rule. We'll study that in the next video and look at those kinds of examples. But hopefully right now you have some idea of how to proceed with complicated integrands and uncomplicating them using the technique of u substitution to help you do that.